Alright, in this video we're going to be working some AP Calculus volume examples, and today we're going to be focused on disks and situations where solids have known cross-sections that are rectangles and squares. So the first one says we've got this region R enclosed by the x-axis and the graph of y equals 3x times 2 minus x. Find the volume of the solid formed by rotating R around the x-axis. Okay, so okay, that's something we can do. So we're going to distribute the 3x over the 2 minus x to get this to a place where we can, maybe anti-differentiate because we don't have any antiderivative product rule. I can already see that coming. Maybe I'll just multiply the 3x on the negative x, make that negative 3x squared plus 6x. Okay, and then if I want to rotate R around the x-axis, we're going to be integrating pi r squared. So remember, volume equals the integral of pi r squared, and if we're rotating around the x-axis or any horizontal axis, we'll be integrating with respect to x. Now we can see on the graph x is going to run from 0 to 2, and I'm just getting you started with some easier ones, but we'll have some more complicated examples as we move forward. Now we're going to need to write down R. But if I think about rotating this region around the x-axis, the radius of each disk would be, reach from the axis of rotation to the far edge of the shaded region. And if I kind of diagrammed that radius, on top, I've got y equals negative 3x squared plus 6x, and on bottom, it's y equals 0. Okay, so the radius is just this 3x squared plus 6x. So all this to say, this is, I'm going to factor out the pi times the integral from 0 to 2 of negative 3x squared plus 6x squared. Okay, so I'm going to need to actually square this before integrating. It's going to be, a little annoying, but something we need to be able to deal with. Okay, that would be negative 18x to the 3, but then there's 2 of them. So it'd be negative 36x to the 3. And then the 6x times 6x would be 36x squared. Oh, now this is going to be something that we can anti-differentiate, except for that 9x to the 4. That's kind of annoying. I can anti-differentiate it. It just won't stay in the realm of integers. So this is going to be pi times 9 over 5x to the 5 minus, that'd be 9x to the 4, 12x to the 3, as x goes from 0 to 2. Okay, so this would be, 2 to the 5 is 32 times 9. Let's just call that 9/5 of 2 to the 5th. Minus 9 times 16 plus 12 times 8. That's a number that you could figure out if you needed. But I think that'll be far enough for us. And if I plug in 0 into that, oh goodness, I left off my pi. There we go. That's a suitable answer, because if I plug in 0 into that antiderivative, I'm going to get 0. So, all right, I've done that one. Rotated around the x-axis. E is enclosed by the coordinate axes, the graph of y equals log x, and the line y equals 1. Find the volume. Okay, so we're going to start by looking at the axis. And we'll be interested in getting the radius after that. The radius will start at the axis and reach the far edge of the region we're rotating. And thinking about on the right, this is going to be, we're going to need an x equals on the left, it's x equals 0. So looking at that, if y equals the natural log of x, then x is going to equal e to the y. And then thinking about the radius being right minus left, that's e to the y minus 0, and that's just going to be e to the y. All right. Volume is pi times the integral of radius squared. Okay. And so think about what I'm squaring, that's going to be e to the y. And I'm going to be integrating as y goes from 0 up to 1. See that? Edges of our region that we're rotating. All right, and then that's, let's see, I've got room over here. Okay, pi times the integral of e to the 2y dy. So we're going to have to prepare for that 2 to come out with the chain rule if I was to take the derivative. So when I anti-differentiate, I'm going to be dividing by 2. So I'm going to have pi over 2 e to the 2y, y going from 0 to 1. I'm just going to leave the pi over 2 factored out. And e to the 2 times 1 minus e to the 2 times 0. And I think that'll be a good place for us to stop. This one does not come with a diagram, so we're going to need to draw one ourselves. All right, so G is going to be the region bounded by y equals 3x minus 3, y equals 3, and x equals 1. Okay, so 3x minus 3. Oh, I think I see how this is going to go. Okay, so 3x minus 3 is a line with positive slope, but kind of a negative y-intercept, so it would intercept the x-axis over kind of in positive x territory. If I think about plugging in x equals 1 into 3x minus 3, I would get 0. So I'm going to kind of just mark off whatever I think x equals 1 is. I'm going to draw in 3x minus 3, whatever I think it's supposed to be right there. And the line x equals 1 is a vertical line. Okay. And then the line y equals 3 is a horizontal line. Okay, just like that. Okay, and we've got this kind of triangle-shaped region right there. That's going to be region G. All right, write but do not evaluate an integral that represents the volume of the solid formed by rotating G about y equals 3. Okay, so that would be if we were rotating around that axis right there. So that would be, the radius would be top minus bottom, y equals 3, y equals 3x minus 3. So radius being top minus bottom, be 3 minus 3x minus 3, and that's going to be 6 minus 3x. Okay, then I'm going to say, okay, that's the radius. Volume is equal to the integral of pi r squared. So 6 minus 3x squared. Okay, we're integrating with respect to x, and it looks like x is going to run from 1 up to, okay, we're going to need to figure out that x coordinate. But we've got enough to figure it out. We look at the two lines that it's on. It's on y equals 3 and y equals 3x minus 3, so I'm going to set them equal to each other. Add 3 to both sides. And I'm going to divide by 3, and I'm going to see, okay, that's x equals 2, so I'm going to be integrating from 1 to 2 if I was integrating, but it said write but don't evaluate, so that's going to be far enough for us. Okay, if we wanted to write an integral that represents the volume of the solid revolving G about x equals 1, okay, that would be, I'm going to just kind of draw the triangle. X equals 1 would be this stuff right here. And so that would be rotating around a vertical axis, so the rectangles would, or the discs would sit horizontally. I'm going to take a representative rectangle right there to get my radius. And on the right, we would be having x equals something, and on the left, it's x equals 1. Okay, now if I had y equals 3x minus 3, and I want to solve for x, I'm going to add 3 to both sides. X is going to equal y divided by 3 plus 3 divided by 3. I don't think I'll just leave it like that. Okay, 1/3 y plus 1. Okay. And so if I'm thinking about that radius being right minus left, that would be radius equaling 1/3 y plus 1 minus the 1. And so it would just be 1/3 of y. And volume is the integral of pi r squared. And this time it would be with respect to y because the radius depends on y, or because we're rotating around a vertical axis like the y-axis. Okay, and then y is definitely starting here at 0 because that's the x-axis. And then up at the top, we had said that was y equals 3 before, so I'll fill that in, and there we go, we're good. Right. Next we've got another situation where it's like part of a parabola. Okay, and we're going to rotate around the vertical line x equals 1, so this will be pretty similar, except we are going to have to actually do the integration. Okay. Right. So we are rotating around this line x equals 1. Okay, the radius on the right. Oh, okay, so if it was y equals x minus 1 squared, okay, I'm going to try to solve for x. I'm going to take the square root of both sides, and that's going to be the square root of y equaling x minus 1. And I'm going to just solve for x and think about the plus or minus after and make sure I've got the right, I'm looking at the right stuff. So that would be x equals 1 plus square root y, I think. And yeah, that makes sense because it would need to be 1 plus the square root of y because we're over here to the right of x equals 1. Okay. So I like that. X equals 1 plus root y. On the left, that looks like x equals 1. Oh yeah, this one's going to work out real nice. And so I'm right here, I'm going to be saying, okay, that's the radius. Radius equals 1 plus root y minus 1, which is just going to be root y. And so we would definitely like to do pi r squared on that. So volume is going to be the integral of pi r squared with respect to y, because we're rotating around a vertical axis again. And y is starting at 0 and ending at 4. And I see that from the graph. So this one they actually want me to take it all the way through, so I'm going to simplify, anti-differentiate, plug in the bounds and subtract. And that would be 8 pi. All right, now I got a couple calculator questions. So I'm going to work these as if we are, answering a question on the quiz or the free response section of the test or the AP exam where we need to justify our answer, which, if we're using a calculator means showing the integral that we're taking on the calculator or possibly showing the equation we're solving on the calculator. So it's talking about y equals e to the 2 minus x squared. Okay. You have to be careful with the parentheses. Sometimes it really doesn't like that. And if you use, in the exponent, so just, sometimes use the parentheses. And then the line y equals 2. So we call it g of x equals 2. Okay, we're going to rotate S, which is going to be this region right here, around the horizontal line y equals 2. Okay, so this is, I'm going to draw a picture of this. Let's say, wait, no, that's the whole point. We're doing disks right now. And it looks about like that. And so the radius would be top minus bottom. So that's going to be e to the 2 minus x squared and y equals 2. Radius is, I just subtract those two from each other. And then that's what's going to get squared, and it's pi r squared. This is going to be dx, and x is going to run from, okay, these are numbers I'm going to have to store in the calculator, but I'm going to, okay, so I see that it was this, this is the positive version of that number. So what I'm going to do is just store the positive version of it and then integrate from like negative a to a or whatever. So call this a, get rid of the 2, And I am going to report that kind of off to the side. So let's say e to the 2 minus x squared equals 2 at x equals 1.14318 and x equals negative 1.14318. All right, and I'll also say let a equal 1.14318. Okay, I'm going to be integrating this from negative a to a. I've got all the pieces. I'll go down here, call for pi times an integral from negative a to a of, okay, radius is top minus bottom, that's f minus g squared dx, and that's going to be 91.784. Okay, a couple of points about this. It's important that we use like actual pi here, not type something like 3.14, okay, because we need to be accurate to 3 decimals. Also, if you round off a to 3 decimals, let's see, okay, so if I change it to 1.143, 1.143 is not as far off from 1.41318 as like 14399 or something. Especially if you'd like truncated, let's just see, it's 7837. Okay, no, that wouldn't have mattered in this case, but I have seen situations, especially with volume, where it produces like kind of large numbers, where it can kind of mess with you in the last decimal. Okay, but that's the nice thing about Desmos, it lets you store the numbers very easily, so there's no point in even taking the risk. All right, so next one, let t be the region of the xy plane bounded by the curve x equals y squared minus y cosine y. Y squared minus y cosine y, and the line x equals 3. Happens if we, okay, so it's just kind of lumpy. If we rotate t around x equals 3. That was pretty awful. That's much better. All right, over here, this is x equals 3. On the left, we have x equals y squared minus y cosine y. Okay, so the radius here is going to be 3 minus y squared plus y cosine y, because I'm subtracting both things. And so that's what I'm going to throw into my integral. Yeah, I was just making sure I'd written the integral I took on the calculator. Pi times, that'd be 3 minus y squared plus y cosine y. And then y, okay, we're going to actually need the bounds, and these are just, okay, these are real numbers. So I'll say that one's B, this one's going to be A. And so I've got the bounds stored. I do need to kind of report that process here. Okay, so describe the equation that I solved. And that was y equals negative 1902 and 1678. All right, and so I'm just going to copy those down. Right, but when I go to integrate, that would be the integral from A up to B of, so you can see it. Did I give that a name? I'm going to call that f of y. Okay, f of y is equal to y squared minus y cosine y. There is x equals 3. So I didn't put in the pi, but I can put it right now. Pi r squared. So r was 3 minus f of y. pi r squared dy, and that's going to be 53.863. All right, the next one's talking about rotating region in the first quadrant bounded by the graph of this y equals square root 400 minus 4x squared and the x and y axes around the y-axis. All right, so we go over here, we look, and in the standard window, I'm not seeing a whole lot of graph. I see a little bit right here. Yeah, there we go. I got my mouse, you can see it there. I'm gonna need to zoom out a little bit. So zoom out until I can see, okay, now I see what's going on. But they're only talking about the first quadrant. So, you know, that actually doesn't matter because I'm going to have to solve this one around anyway because we're rotating around the y-axis. But select this. This is a good one. So, looks like curve. And, you know, what we might be wise to do is 0, 20, 10, and 0. We've got the calculator. We might as well use it. Okay, we're going to revolve around the y-axis, so that's going to be my axis of rotation, and the region is touching the whole time, so it means it's going to be a disk scenario. Okay, I've got the radius on the right. I'm going to need an equation for x. On the left is the y-axis. That's x equals 0. So I really just need to solve this equation back for x. So y squared equals 400 minus 4x squared. Let's say, maybe add the 4x squared over here and subtract the y squared over to the other side. Divide by 4 maybe. 100 minus 1/4 y squared. Then I'm going to take the square root of both sides and then kind of check for reasonableness. All right, yes, x is equal to a positive number because I'm working in the first quadrant, so I want the positive square root. And then there I've got it. Okay, so x is the square root of 100 minus 1/4 y squared. Okay. So what I'm going to need to do, I'm just going to be running an integral now. I guess that's, radius is going to be that, so, you know, I might as well just copy that and start in my integral here. Oh, this is one, I guess we could have done this one without a calculator, but I think I've seen a multiple choice question like this one that had decimal answer choices. So that's my radius. I'm going to square it, integrate pi r squared, and y goes from 0 to 20. That's going to be a job for the calculator though, to get a decimal number. So I'm going to take pi times the integral from 0 to 20 of, okay, get rid of the square root in the square, 100 minus 1/4 y squared dy. Okay, it seems pretty reasonable. I mean, it's, yeah, 20 and 10, that's going to be pretty big. Think about that. All right, yes, I compared that to like a similar cone, and it was kind of, I mean, in the same area. So I've got, this is 4188.790. Next we are, okay, we're on to the cross sections. So, okay, I'm going to get rid of the calculator, but I am going to bring something else in. All right, so I added the little GeoGebra applet on the right where the calculator was, so I can give you at least a rendering of some of these solids with known cross sections. But for now, I'm going to work it, you know, without a calculator like it says, and then the stuff in the bottom is really just for us to visualize. So, all right, y equals x squared, and y equals x. Okay, well, that doesn't look great. Okay, what is, let me see if I can get that to look better. All right, there we go. So each cross-section perpendicular to the x-axis is a square. So I'm going to take a cross-section perpendicular to the x-axis. I'm going to think about top and bottom. This was y equals x, and this was y equals x squared. Oh, goodness. This is very laggy. All right, I think what I'm going to do is I'm going to see, how do I do? Oh, it's that play button right there. All right, so what's going to happen is it's going to show all of these slices filling up as that vertical bar goes from 0 to 1. And then we're getting ourselves a solid, and see it's bouncing back, and I don't think we need to keep watching it much past that. But if it does let me kind of, move around, and that's going to be a square at each point where we're perpendicular to the x-axis. And as you can see, this is not the type of shape we see very often. Okay, so I think I'm going to leave it at that for the GeoGebra app, and then I'm going to come back on that at the end of the video and do all the rest of the cross sections all together, in case that's what's causing my image to not look as good. All right, we know that the area of a square is the base squared. This is the base right here that we've got in the region. So base is equal to top minus bottom. Area is base squared. And we're going to need to square that anyway. So, all right, x times x is x squared. X times negative x squared would be negative x to the 3, but I'm going to have 2 of those. And then negative x squared would be positive x to the 4. All right, that's our area formula. Remember that with known cross sections, volume is equal to the integral of the area formula, in this case with respect to x. So that area was, I don't know how I was supposed to fit that. X squared minus 2x cubed plus x to the 4 dx, x going from 0 to 1. There's no pi on this one because there's no pi in the formula for the area of a square. Let's see. Well, at least you can see my handwriting. All right, now I'm going to anti-differentiate. Oh, some common denominator work coming. When I plug in 1, I'm going to get 1/3 minus 1/2 plus 1/5. And goodness, it really is going to be 30s. Okay, now this would be a safe place to stop on the quiz of the test, and I'm going to have to reset the connection here in a minute. Be a big deal for you, but if I needed to get that to a common denominator, that's 10 out of 30 minus 15 out of 30 is net negative 5 out of 30 plus 6 out of 30. I feel like that's going to be positive 1 over 30. All right, now this one is going to be a calculated problem. The base of the solid is the region of the first quadrant bounded by the coordinate axes in the graph of 5 minus x over 1 plus x. So I'm going to think about what that graph looks like. Maybe do some graphing. 5 over 1 plus x. So that's 5 minus x over 1 plus x. There we go. All right, so if I zoom in on the action there. All right, let's see what's going on. Got kind of something like that. I might take note of the intercepts. That would be 5 and 5. Yeah, that makes a lot of sense, thinking about the graph and the equation. Okay. Not showing the writing very well. Okay, you can see shadows of my writing. All right, I'm struggling here. I might have to call this one and record this homework in 2 separate videos after this one. But cross sections perpendicular to the x-axis are rectangles. Okay, so that's going to be the base of the rectangle. The height is 4 times its width in the xy plane. I'm going to call that width. Width is going to be top minus bottom. That's just 5 minus x over 1 plus x. because it goes down to the x-axis, which is y is 0. Height is 4 times the width. Okay, and we know that the area of a rectangle is the width times the height, so that's equal to 4 times the width squared. All right, so I'm thinking 4 times that fraction squared, 5 minus x over 1 plus x squared. Okay, and you can see very little to possibly none of that. Let's see, there you go. All right, so that's what I'm going to want to integrate. Definitely going to want to use the calculator for that. But volume is the integral of the area formula, so 4 times that fraction squared. And we're going to integrate x from 0 to 5. All right, let's see. Move it around a little bit, makes it worse. Oh boy, yeah. Okay, that's as good as I got. Let's see, I've got an idea. Let's just really enlarge the calculator here and watch me do that instead. So, all right, the integral from 0 up to 5 of 4 times 5 minus x over 1 plus x. Squaring that, integrating with respect to x, 53.995 or 53.996. All right, that's going to be all for this video. I'm going to record the rest of the problems on this homework in a separate one.